Hi guys. Today I'm going to go through the lesson with you on limiting reactants. So yesterday after your test you would have written some of these out. So most of you, depending when you finished your test, I guess, will have some of these notes copied down. Others maybe didn't get to it. So I'm just going to go through the lesson anyways, like writing out all the blanks and most importantly doing the examples with you. So limiting reactants are kind of the final piece to the puzzle in stoichiometry. We start to put all of our skills that we've been learning for the last number of weeks together. And we're still, basically applying all the different conversions that we've been working with to a chemical reaction, but we're just taking a tiny bit different spin on it than we have before this. So let me give you a little bit of background and then we'll do some examples together. So most of the time in chemistry, we have an excess amount of one reactant, which just simply means that there's too much of it, and after the reaction's over, that excess amount is just left over. It's sitting there unreacted. Okay, the other reactant limits how much product we get. Once it runs out, the reaction stops, and we call this one the limiting reactant. So basically the idea is generally in a chemical reaction, there are two reactants, not always, but in the ones that we're going to be looking at, that's the case. So in those two reactants, when you measure out your quantities and put them together in whatever way they need to be put together, like add one to the other, and the reaction starts to happen, as those reactants are reacting with each other, which is basically just means their atoms are recombining and rearranging, what happens is one of the reactants gets completely used up before the other one. So when one reactant gets used up, that causes the reaction to stop. And the reason for that would be because now the other reactant has nothing left to react with. So the limiting reactant is the reactant that runs out first. And because it runs out first, it's the one that determines how much product we're going to get. So once we learn about this limiting reactant, it's very important that all of our calculations that we do in stoichiometry are done using the amount given of the limiting reactant, because that's what's going to give us an accurate picture of how much product is going to be produced. So just to kind of wrap our heads around that concept, let's look at something that's like not a chemistry example, just to make sense of what this means. So let's say you want to make sandwiches for a picnic, and we're going to pretend that the sandwiches that we are making are very, very specific. We cannot improvise whatsoever. So for these sandwiches, we would need 2 slices of bread, 2 slices of meat, and 1 slice of cheese. And that's the way the sandwich has to be. Okay, so what we have at home when we're preparing for this picnic is 10 slices of bread, 12 slices of meat, and 8 slices of cheese. So based on the supplies that we have at home and this very specific recipe for a sandwich, how many sandwiches could we make? Okay, so because each sandwich needs 2 slices of bread, the bread amount that we have tells us that we can make 5 sandwiches. Okay, so let's just write this out. Well, we can make 5 sandwiches. Okay, so let's say, well, with those 5 sandwiches, each one is going to have 2 slices of meat. So of our 12 slices of meat, we only use 10, and each one has 1 slice of cheese. So out of our 8 slices of cheese, we would only use 5. Okay, so what we would say in this case is we have some leftovers. The leftovers would be those 2 slices of meat and the 3 slices of cheese. So this would be if we're making an analogy here, this would be comparable to the reactant that is in excess, the one that's left over after the reaction's finished. So we don't actually use those. They're just sitting there, still the same as they were before. What limits the amount of sandwiches is the bread. Okay, so I'll just write that here. The bread, limits the number of sandwiches you make. Okay, so in this analogy, the bread is the limiting reactant and the meat and cheese are the excess reactants. We can't make any more sandwiches than this bread allows us to make. Okay, so the amount of bread is what determines how much product we get. And our product in this case is sandwiches, but in chemistry, our product would be some sort of chemical compound, or not necessarily compound, but some sort of chemical, right? So this is kind of an easy way to understand it because I think we can all wrap our heads around this scenario. So you can also compare, and I think I have mentioned this at some point before, that you can also compare chemistry to recipes. So a chemical reaction is very much like a recipe. If you add a certain amount of one reactant and a certain amount of another reactant, you can determine how much product you can get. So just like a chocolate chip cookie recipe, here's our recipe. If we add these ingredients in these amounts, we will get 3 dozen cookies. Of course, cookies can vary in size, but let's pretend that they are a standard size and 3 dozen is what we're going to yield from this recipe. So if we had the specified amount of ingredients listed, could we make 4 dozen cookies? Well, no, we couldn't. No, because we only have the ingredients for 3 dozen. So I'll say recipe yields 3 dozen. What if we had 6 eggs and twice as much of everything else? Could we make 9 dozen? Well, it takes 2 eggs to make 3 dozen. So 6 eggs would make 3 times, so 9 dozen, but we don't have 3 times as much of everything else. We only have twice as much of everything else. So the maximum amount of cookies we could make with this amount of stuff is 6 dozen. So no, we could only make 6 dozen. Okay, what if we only had 1 egg? Could we still make the 3 dozen cookies? Nope, recipe calls for 2, so no. No, we need 2 eggs to make 3 dozen. Okay, so it's a comparable situation, whether you're talking about sandwiches or cookies or chemistry, to what happens in a chemical reaction. So what do we do when we have a reaction in front of us? How do we know which one of the reactants is limiting? So when this says to find the correct answer, what I mean by that is to find the limiting reactant, we have to try all of the reactants. And most of the time there's 2. So we have to calculate how much product we can get from each of the reactants to determine which one is the limiting one. Okay, the lower amount of product, okay, so once we test both reactants, we'll see, okay, how much product are we getting from each one? The one that produces the least amount of product is our limiting reactant. So that's what this next statement says. The reactant that makes the least amount of product is the limiting reactant. Once you determine the limiting reactant, it should always be used to determine how much product is made. So once we know this limiting reactant, all of our stoichiometry calculations are based off of the amount of limiting reactant. Because if you went and used the excess reactant to do your calculations, it would tell you it would give you too much product. And that's actually impossible in that given situation. So I think this will become a lot more clear once we do an example. Another thing to make sure is make sure when you're comparing how much product is made by each reactant, make sure you're comparing the same product. So choose one product. Sometimes there's more than one product. So pick one, make sure you're comparing apples to apples, basically, right? If you're comparing one product to a different product, that's not a reasonable comparison. It won't tell you really anything. So to understand all those rules, let's actually do an example together. Now, I think I left this one filled in. So you may already have this filled in your notes if you filled them in yesterday. If not, fill them in along with me. If you do have, just follow what I'm doing and just watch. Okay, so we're told 10 grams of aluminum reacts with 35 grams of chlorine gas to produce aluminum chloride. Which reactant is limiting, which is in excess, and how much product is produced? Okay, so here's the reaction. It's already written out for you and it's already balanced. Now notice we are told 10 grams of aluminum as well as 35 grams of chlorine. So we have amounts of both reactants. Up until this point, we've never been given that information. We're always just given one amount of one thing, either a reactant or product. That's what we've dealt with up until this point in stoichiometry. So now we're being told, okay, we're mixing 10 grams of aluminum with 35 grams of chlorine gas. So we want to know which one of these two limits this reaction and therefore tells us how much product we're going to get, how much aluminum chloride we're going to get. So what I would do is I would take my 10 grams of aluminum, that's what I'm going to start with, and just simply because that's the first one given to me. And I'm eventually wanting to know how much product is produced. Now, it doesn't really give me like a unit. In this case, I'm just going to assume grams, like a mass, just because that's a practical unit that we can measure in the lab. So I'm going to convert to grams of aluminum chloride. Okay, so I want to see if all 10 grams of aluminum react, how many grams of aluminum chloride am I going to get? So I want to switch from aluminum over to aluminum chloride. I know I can't make that switch unless I'm in moles. So I'm going to convert from grams of aluminum to moles of aluminum. So this is where I'd use the molar mass. How many grams are in 1 mole? Well, looking at the periodic table, there's 26.98 grams in 1 mole. Okay, so that gets me to moles of aluminum. Now, I want to switch from aluminum over to aluminum chloride. That's what I want to know about. I want to know about my product. In this case, there is only one product because this is a synthesis reaction. So I don't have to make any decisions here about which product to choose. So I'm going to switch from moles of aluminum over to moles of aluminum chloride. Now remember, this is the mole ratio step. So I pull these numbers, the coefficients, from the balanced reaction. So it happens to be a 2-to-2 ratio or a 1-to-1 ratio. So this step isn't really going to change anything mathematically, but it's just basically a record-keeping step. Now we're in aluminum chloride. So in order to get a helpful, measurable amount of aluminum chloride, I'm going to switch over to grams of aluminum chloride. Okay, so in 1 mole, how many grams of aluminum chloride are there? So I'm going to take aluminum's mass plus 3 times chlorine's mass, which is 133.33. Okay, so I'm going to go 10 divided by 26.98. This step's not going to do anything. And then multiply by 133.33. So when I do that, I get 49.42 grams of aluminum chloride. Now what I just did here is something you already know how to do. It's just a mass to mass question. You've done that before. The only difference is usually your question would end here. This would be your answer. But in this case, because we don't know which one's limiting, we're going to test both. So we've tested aluminum and we said if all 10 grams of aluminum react, this is how much product we'd get. Now let's compare that to chlorine. So we have 35 grams of chlorine. So I'm going to go through the same set of steps. I'm going to work my way from chlorine over to grams of aluminum chloride so I can compare those two amounts. So again, I need to get to moles first. So in 1 mole of chlorine, I would just 2 times the mass of chlorine would give me 70.9 grams. Okay. Once I'm in moles, then I can switch over from moles of chlorine over to moles of aluminum chloride. Again, I'm going to pull these coefficients from the balanced equation. So I've got a 3 in front of chlorine and a 2 in front of aluminum chloride. So it's a 2-to-3 ratio. And finally, I'm going to go to grams from moles to grams of aluminum chloride. So I can use the same molar mass that I've already determined up here. Okay, so 35 divided by 70.9 times 2 divided by 3 times 133.33 gives me 43.88 grams of aluminum chloride. Okay, so now I'm ready to compare my two amounts. Aluminum would produce, if 10 grams of aluminum fully reacted, I'd get 49.42 grams. And if 35 grams of chlorine fully reacted, I'd get 43.88 grams. So this tells me that it must be chlorine that's my limiting reactant because it is going to run out first because it produces the least amount of product. So chlorine will run out first, which means this is the actual amount of product that we get, 43.88 grams. This is not accurate because not all 10 grams of aluminum react. There's going to be some aluminum left over. So we can answer all of these questions now from doing these 2 mole to mole stoichiometry calculations. So what I want to say then is chlorine is the limiting reactant. Okay, which means that aluminum is in excess. So there's going to be some aluminum left over when the reaction's finished. And the amount of product produced is the lower amount produced by the limiting reactant. So 43.88 grams of aluminum chloride is produced. Okay, so you know how to do all of this. It's now just interpreting it slightly differently. Let's try another example. I'm quite sure I left this one blank, so I don't think anyone would have this written down yet. So we can work along through this one together. So this one says 15 grams of potassium reacts with 15 grams of iodine. Calculate which reactant is limiting and how much product is made. Okay, so very similar question to above. But we do have to write out our balanced equation first. It's not given to us. So I know potassium reacts with iodine. So remember, iodine is a Hofsprinkle. So when it's by itself, it's diatomic. We add the 2. Okay, so if those are our only 2 reactants, this has to be a synthesis reaction, meaning potassium and iodine will simply combine to form potassium iodide, right? And I know it is Ki because K is a +1 ion and I is a -1 ion. So now I just need to balance this. So I'm going to put a 2 here to balance out iodine and a 2 here to balance out potassium. Okay, so I again have amounts of each of my reactants. And again, there is only the one product here to go to. So I have no choice. I'm going to convert to potassium iodide. And I want to, even though it doesn't ask me how much, like in what unit I'm going to for potassium iodide, I'm just going to assume grams, okay? Grams of potassium iodide. So let's compare. So I'll take my 15 grams of potassium. So in order to switch from potassium over to potassium iodide, I need to be in moles. So in 1 mole, this would just come straight from your periodic table. There would be 39.1 grams. So that gets me from grams to moles. Now that I'm in moles, I can switch from potassium over to moles of potassium iodide. So this is where I would use my coefficients from the balanced equation. And finally, I'm going to convert to something measurable, which would be grams. Okay, so this is the molar mass step. How many grams are in 1 mole? So if I add potassium's mass to iodine's mass, it actually works out to 166 on the nose. So I'm going to divide by 39.1. This step does nothing, and then multiply by 166. So that gives me 63.68 grams of Ki. So now that would be if all 15 grams of potassium react. We don't know if it does yet. So let's compare to the 15 grams of iodine. Okay, let's see what happens if all the iodine reacts. So same set of steps. Get into moles so that you can switch substances. So the molar mass of iodine, I'm going to double the mass of iodine from the periodic table. So that's 253.8. And then I'll use my mole ratio step to get from iodine to potassium iodide. Okay, so I want to pull my coefficients here. Iodine's a 1, potassium iodide's a 2, so a 2-to-1 ratio. And finally, I want to get into grams so I can compare my amounts. So the last step here is the same as the last step here. All right, so 15 divided by 253.8 times 2 times 166 equals 19.62 grams. So this time, the amounts are actually significantly different. Iodine, if all of this iodine reacts, it produces way less product than the potassium. So that's probably an indication that we added way too much potassium and there's going to be quite a bit left over at the end. Okay, so this amount is impossible because this is going to run out first. So this is going to be left over. So let's answer those same questions again. The limiting reactant is the reactant that produces the least amount of product. So iodine is the limiting reactant, which means potassium is in excess, and the amount of product that we can actually expect to get is this amount here. So 19.62 grams of Ki is produced. All right. Now, that I'm not going to do that last little bit, finding the amount of excess today. We'll save that for tomorrow. It's just good to get a handle on this first before we add in another layer. So I'm just going to pull up your assignment that you'll find after the notes. Okay, so it's this limiting, it's kind of a bit ugly looking, but this limiting reagent worksheet number 1. Reagent's just another word for reactant. Okay, so I just wanted to explain a couple things about this because both of the examples in the notes had only one product. So it's important to realize that if you're working out the limiting reactant or limiting reagent and you're comparing, so in this case, propane to oxygen, you want to just choose one of the products to convert to. And it actually does not matter whether you choose carbon dioxide or water. It will still tell you accurately which one's the limiting reactant. It's just important that if you choose carbon dioxide, that you convert the 14.8 grams of propane to grams of carbon dioxide, and also the 3.44 grams of oxygen also to grams of carbon dioxide. If you do one to carbon dioxide and the other to water, then they're not comparable, right? It wouldn't make sense to compare them. So you have to just choose one product and stick with it. Now, what I always tell students is look ahead in the question, because these limiting reactant problems are a lot of work and they're time consuming. So you want to save yourself some work. So if you look ahead, that often helps you make your decision, because usually one of the products is being asked about. Now, unfortunately, in this case, you're being asked about carbon dioxide and about water. But if I look ahead here, I'm being asked about the amount of the moles of carbon dioxide produced and the grams of water produced. So grams, the one that's talking about grams is probably the one I would choose. So when I do this step here, compare the 14.8 grams of propane, I would go to grams of water, and the 3.44 grams of oxygen, I'd go to grams of water, because then I'll have done all the work I need to answer part C. Once you've figured out which one is the limiting reagent, you want to make sure when you go to do this extra separate calculation here for part B, you choose the limiting reagent. So for example, let's say, I can't remember in this case which one is the limiting reagent, but let's say it's propane. Okay, let's say we determine from all our work in part A that it's propane. Then when I go to do how many moles of carbon dioxide are produced, I want to go from the 14.8 grams of propane into moles of CO2. That's just very important, because that's what's going to give you the accurate amount of product. Okay, so I want you to work through these questions on this page. I will have the answer key posted on Brightspace. So if you do get stuck, you can refer to that, or after you've gone through a question, you can compare it to the answer key to see if you're on the right track. And then tomorrow, what I'll do is we will go through how to calculate the amount of excess reactant that's left over.